Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Yasuhiro Yokota and Deborah Domingue with us today. Hey, Yasu. Hi, Deborah.
Hey.
Hello. Thank you, Frank.
Well, thank you very much for agreeing to talk about your really lovely Planetary Science Journal article. It's a very nice one. And the topic is really exciting, so it's great. Deborah, where are you located at?
I'm just north of Baltimore, Maryland.
Okay.
A little town called Bel Air.
And Yasu, where are you located at?
I'm at the Sagamihara city. It's near to Tokyo in Japan.
Very cool. And for everyone watching, it is September 14th, at least in the US. It's September 15th where Yasu is. So we've gone across the date line. Let's see. Yasu, how is the summer in Japan? Has fall started, or is it still summer in Japan?
These few years, Japan is this summer is terribly hot, but this year also there is some also hot time, but now it's become a bit better.
A little better. Okay.
Yeah.
We are still quite hot in Phoenix, where I'm at, and it won't cool down until typically October is when we start to cool off a little bit. So, Deborah, are the leaves starting to turn on the east, or are we still in the summer mode?
We're still a little too far south to see the leaves starting to change color.
Okay.
We'll get that probably mid-October.
Okay.
But this is the time of year where you have very hot days, followed by very cool days, followed by very hot days.
Shift has
started.
started.
So it decides which way to go.
Shift has started. And Yasu, that's a pretty awesome poster behind you there. That is a great poster.
Oh yes, it is poster of the moon of the. It's taken by, I think, lunar reconnaissance orbiter.
Oh yeah. Okay. Sure. Very cool. Very cool. Let's see. Let's start with Yasu. Yasu, since you're the prime here, what do you like to do for research?
I'm mainly doing image analysis of the planetary images, both topography and especially in the photometric study.
Cool. Very nice.
And yes, I did some lunar work before, and since few years ago, I joined the Hayabusa 2 project.
Very nice. Very nice. Deborah, how about you? What do you like to do for research?
So I'm one of these people. I have a toolbox. I'll travel the solar system.
Excellent.
Toolbox. In my toolbox is spectroscopy. There's spectral analyses, both with color image data and with spectral measurements. But my overlap with Yokota-san is I also do photometry.
Ooh, okay.
And that's the study of how surfaces reflect light depending on illumination and viewing geometry.
Cool. Cool. And what objects in the solar system have you applied this toolbox to? So
I tend to look at bodies without atmospheres. So Mercury, Moon, icy satellites, asteroids, variety.
Nice. And that is going to bring us to this very lovely Planetary Science Journal article, Opposition Observations of 1621-73, Ryugu, Normal Albedo Map highlights variations in regolith characteristics. And Yasu, take us away.
Yes. Well, first of all, Frank, thank you very much for give us this chance, and I'd like to say thank you for the Hayabusa 2 people that who realize such wonderful observations. And
Yeah.
yeah, and
Good.
yeah, is it Franco? Is it better to introduce those people all?
I think just a thank you, Global. I think
Okay. Yeah.
that's perfectly great. Just thank the people who are on the paper.
Mm-hmm. And we team is a very large team, and we take about, I think, 2 years to to publish this paper.
Okay.
I think, yeah.
Yes, indeed. Okay.
Okay.
Mhm.
And the next, should I get into the inside of the article?
Yeah.
Oh,
Yokota-san, what are some of the key findings that you really liked about that came out of this paper?
yes. This paper is using the opposition data of the asteroid Ryugu by using this camera ONCT, and our most important result is we made a map of the normal albedo of the Ryugu.
Mhm.
So
Want to put a figure up at this point?
I think, yes. Could you skip to the figure 8?
I certainly can, and I certainly will. Figure 8 in 5, 6, 7, and 8. There we go. Lovely. Very nice.
Thank you very much. And this is a V-band map. I mean, 0.55 micron band map. The Ryugu is about asteroid with about 900 diameters, and so this is a simple cylindrical map of the normal albedo. The normal albedo is a reflectance defined at phase angle 0.
Okay.
And
what's really unique about this is that this is based on observations. And it's very rare to have observations at opposition, enough to be able to form a map like this.
Yeah, it's lovely. Very nice.
Yes, using the opposition data, shadow or due to the topography is avoided. And next, we please go to figure, I think, 10. This figure 10 is, this is a figure 10A is a full scala map made from 3 bands of the camera. So we derive the normal albedo at the 7 band of the in the visible wavelengths. So we derived the multispectral map for the Ryugu. So this is our most important result, that this multispectral map become the base of the people future analysis of the research of the Ryugu.
Are there particular features in this map that you would like to call out, or?
Yes, actually, we can find many things from this multispectral map, but
Okay.
so the one particular important things is that I think there are bright areas in the higher latitude regions. So yes, now your pointer shows one of them, very bright part in the northern part of the Ryugu, and there are also bright part in the south part. Yes, that part. Yes. We thought we think that these regions is a lower degree of the space weathering.
Okay.
Or such kind of something alteration, low degree of alteration.
Okay.
And well,
what do you think makes for the lower albedo in these two regions? Is that ice?
Oh no, I mean Ryugu is a C-type asteroid. It's very dark, and even if in this figure it is the brightness is very enhanced.
Okay.
So when we see in actual color, it may be very dark and black.
So to give some idea, Ryugu reflects maybe 4% of the light that shines on it.
Wow.
Yeah.
It's an extremely dark object.
Yeah.
And as Yokota-san said, the albedo here is stretched. The differences are not large. It's not like you have a patch of ice and a patch of charcoal next to each other.
Right.
It's all very dark. And as Yokota-san said, the differences are, especially at the high latitudes, is due to space weathering, interactions with the solar wind, radiating the surface. It's a little less radiated. So it shows differences in regolith processing.
And just as a reminder for...
Would you agree with those statements, Yokota-san?
Yes, of course. Thank you, Deborah.
And just as a reminder to folks, how big is Ryugu?
It's just 900 meters diameter.
Okay.
Oh, I remember I have I mean not mine, but in our laboratory we have the small figure of the Ryugu. So just few seconds.
It'll be fun to see.
Okay, so we're going to take a little time out, and so all this.
No, he's off to get a model of the asteroid. It's really fun.
This is good. Oh, we gotta. Okay, I'm going to come out of
the show and tell.
Yeah,
I'm going to come out of the share. Go ahead and put that up. Oh, that is awesome.
This is 3D model of the asteroid Ryugu. So it has this kind of diamond shape.
Yeah.
It's similar to Bennu.
Very nice. Is that it from 3D printing, or is that?
Yes,
it is
3D 3D printing.
Awesome. Very cool.
But this black color is just a material, I mean plastic or something. But the actual Ryugu might be similar to this kind of darkness.
That is. Go ahead.
And the model is really cool because if you bring it close to the camera, you can see some of the larger boulders on it.
Ooh.
Oh, yeah, yes. This is made from the actual topographic data. So those boulders are
real.
Real.
Yes.
Okay.
Their positioning is accurate. Yes, and their relief is accurate. Very cool. That is awesome. Can I buy one?
Not yet, because this is made in this institute.
Okay.
So
you have a bestseller there, I think. Very cool.
Yeah.
Thank you so much for sharing that.
Thank you.
That's the greatest thing.
Fun.
That is the greatest thing ever. Okay, and we are back to the 2D world of the albedo maps. So you thought the albedos was one of the main results, and what do you think might be another of the major results?
Well, so Yokota-san, what are some of the key findings that you got from these color maps, these normal albedo color maps?
Yes.
Spectral.
We have many findings, but these are listed in the conclusions section of this paper. So shall we see?
Let's take a look at those, just to make it easy. There you go. Our results include. Okay.
Okay. Thank you. At first, oh yeah, there's 10 list, 10 topics in this list, but yes.
Which one would you like to talk about? You want me to pick one?
Okay. I'd like to introduce number one first. We found a strong negative correlation between the spectral slope and V-band albedo. I mean, spectral slope means when we plot the reflectance spectra, then we can define the slope of the plot graph. And I mean, when the longer wavelengths have a relatively high reflectance, then we call it the spectrum is red.
Okay.
Or in the opposite way, then we call it spectrum is blue. Such slope we defined as a BX slope. I mean, blue to expand, it's near to infrared. So we found the slope of the spectra is have a negative correlation with 0.55 micron wavelength albedo. And well,
is that a large negative correlation? How does that compare?
Yes, it's very very strong correlation, but and figure is shown in, well, figure 11.
Let's go to figure 11. It's a long paper, people. but read it. It's awesome. Figure 11. Not quite.
Sorry, I skipped many things, but
No, it's fine.
figure 11.
It's all good. It's all good. Okay, figure 11.
Yes, yes.
Okay.
Figure 11A is we show the correlation between 0.55 normal albedo and spectral slope.
Okay.
Yes, and in the previous studies, it is also pointed out as this panel B, but in the previous studies, they did not use opposition observation, and it many topographies, shadows, or such kind of thing is affect to the measurement. So when we use the opposition data, then we derive very low noise map, and the relationship become very clear as the left side panel.
Yep, that is clear correlation.
Yeah.
Okay.
Yeah. And yeah, we found that also these two this strong correlation is mainly controlled by the shorter wavelengths albedo. So longer wavelengths albedo is not so change, but shorter wavelengths albedo become large variation in place to place. So the plot like is become controlled by shorter wavelengths like this way.
Okay, I'm with you. I'm good. Yes.
But we found some small places have a variation in the 0.95 micron.
Okay.
So we use the 0.95 micron as another indicator of some spectral variation. So
that would be this panel here, panel C.
Yes, but and this become another important findings that I think another figure. Well,
is
figure 18 is maybe
one question on panels.
Yes.
Is the red line a best fit?
Yes, but this time this correlation become much weaker than the panel A. But this means there is a something another effect. I mean, exists. So it means spectral slope and 0.95 micron normal albedo has something independent information.
Yes. Okay. Okay. Thank you. Okay. Figure 18. Let's go to figure.
Okay.
Give me one sec. Where are we at? 17. Good guess. Ooh, nice. Okay. Figure 18. We got 3 panels.
Yes.
Let's just start at the top and we'll
probably we better to focus on left side panels that aiming this A panel. Yes.
Before you go on, Yokota-san,
yes,
might want to say something about why we look at the slope versus the visible reflectance. Or the reflected. It's a way to measure the degree of weathering on a surface. correct?
Yeah, yes, you're
Yeah.
right.
So that's why we take a look at why are they correlated and how strong are they correlated. It tells us about how mature the surface is.
Got it. Thank you.
Yes, we want to know the variety of the spectral variation on the surface, and it includes space weathering, or if some material variation exists, then such kind of thing we expected to find, but when we plot the spectral indexes into this way, I mean, horizontal axis is 0.95 micron albedo, and the vertical axis is the spectral slope.
Yes.
And there is some color plots on this figure, color symbols. This means is taken from different places on the Ryugu.
Okay.
Some places is relatively darker place, and some places such as this blue symbols is taken from the high latitude, higher albedo places.
Right. We saw that in the maps.
Yes, yeah.
Good. Okay.
And we found that those places have some trend in this figure. So we think that this trend indicate different degree of space weathering.
Okay.
So this yes, lower part is has a fresh surface,
Okay.
and probably when the weathering occurred, then the spectral moved to the upper side.
Right. Okay. That makes sense. Okay.
This is one of our findings, and that we identified the spectral change trend. And another important thing is we can see it in panel C. It's
boulders.
Yes, this time we take a spectral of some boulders, and there are some boulders which have in this figure it is indicated as trend B. Some boulders have branches into the right side of the figure. These boulders has a bright albedos, and it is recognized also in previous studies. So these are marked with pink triangles, and we found these boulders have a different branch, and so we found such different trend, and our hypothesis is that this is a different kind of alternation, and we think that the trend B indicates probably some heating alteration.
Interesting.
So the idea is the two different trends say something about that maybe different boulders experience different processes to weather them.
Cool.
Yeah.
Cool.
Yes. So this trend B borders which belongs to this trend B is not majority, minor of the on the Ryugu, but we hope that this kind of two trend will be seen in the returned samples reflectance.
Yes.
Yeah. And we can connect the returned sample and actual distribution on the Ryugu. Then.
When do the return samples come?
Oh, it's already come back to us, but I and Deborah is not the member of the analysis team, sample analysis team, but we hope our colleague will find this kind of
Trend.
Yes, trend.
Yes. Yes.
One of the things that Yokota-san and I do is we study the surface. We know what the sample sites look like. We characterize them. We characterize the whole surface. So when the sample analyses come back and say the sample sites are like this, then we're able to extrapolate that to the entire surface.
Got it. Cool. Very nice. Thank you. Okay.
Okay.
Other major findings, or do you want to carry on with?
Okay. Then I skipped many things, but I like to show the principal component analysis results. Maybe it's figure 20 of this article.
And PCA.
Yeah, a PCA.
There you go. There's 20. I'll blow that up a little bit. There we go. Okay.
Yes.
Money shot.
Yes. This part is mainly led by our co-author Eri Tatsumi, and she correct the spectra of the many other asteroids from ground observations, and executed the PCA analysis. And this black clouds means Ryugu data. So this horizontal axis is component 1, and vertical axis is component 2. And then Ryugu surface distributed like this, and this some color triangles and color circles means places on the Ryugu. Yeah. And this star-shaped symbol are the candidates of the Ryugu's parent families.
Okay.
In the previous studies, which is proposed in previous studies, there is a Eulalia and Eulalia family and Polana family and Erigone family, and this kind of PC analysis shows that from our spectral data, Ryugu seems to be very similar to Eulalia family or Polana family, and possibly Erigone family is a bit far from this group.
Right. Question?
Oh yes, please.
Do the principal components 1 and 2, do they have a physical interpretation?
Oh.
Can I say
well, so, in using this study, we use the normalized spectra, and so I think component 1 or 2 may correspond to slope or some kind of such kind of I mean spectral slope or such kind of shape of the spectra.
Okay.
But and I think it's created with material, but it's difficult to interpret much detail, I think.
Okay.
Yeah, the principal components are sort of related to properties.
Yeah.
But not
Totally.
definitively a property, because otherwise you could just use the property.
Use that property.
Yeah.
Okay.
What's really nice about this particular diagram, it not only compares Ryugu and specific places of Ryugu with the potential asteroid parent bodies,
right?
But it also compares it with different meteorite types, and those are what the colored circles. Yep. Yes.
Yep.
So it really is a thorough comparison.
Very beautiful.
With meteorite samples that we have, and with the telescopic observations. So it's a really nice comparative piece of work.
It's beautiful. Beautiful. And then we have another one down here as well.
Yes. Yes. This time the vertical axis is component 3, and
yeah.
And in this case also it shows the Erigone family might be different from the Ryugu's distribution.
Yeah, one sticks out a little bit there. Yeah, the blue one does too. They both kind of stick out.
Yeah.
Sort of, not terribly.
Euralia is very close to the Ryugu's data, but Polana is also still remains as a candidate.
Okay. Nice. Very nice.
So yes, I think these are the main findings from this Albedo map currently, but I think this map may be useful for have a much potential. These maps have much potential to much more findings.
Yes.
What will be interesting is once they have the sample analyses to see where the sample analyses would fall.
Right.
Here.
Right. Actual laboratory astrophysics. Yes.
Yeah.
Okay. Yasu, anything else you would like to cover?
Yes.
There's our 10.
Sorry. I skipped almost the introduction or method place, but I'd like to show figure. I mean, figure 3.
Figure 3.
for how the Ryugu looks like in the opposition observation.
Yes, very nice.
Yeah. Yes. We use this kind of images to make the map, and panel A is not opposition observation. It's taken from taken at the solar phase angle 19 degree.
Okay. Yes.
Yes, we can see many topographic shadows on the Ryugu surface, but phase 90-degree phase angle is not so large phase angle for other planetary bodies observation, but of course Ryugu is has a so rocky surface, so 19 degrees not enough to eliminate the shadows.
Okay.
So when we move the spacecraft into the opposition condition in this special observation, then we can derive this the images like panel B. So it is flat, or it's like a full moon image.
Yes. Yes.
Yes. Then we in this situation, the shadow is eliminated, and when we enhance this image, then it looks like the panel C, and we can derive the albedo difference in very low noise.
Cool. So the red here is a marker.
Oh yes, it is. Yes, this is interesting thing in the Hybe-Satu operation, that before the sampling of the material, before the landing of the spacecraft, we dropped the target marker. It's about 10 centimeter sphere with retro-reflective material.
Got it.
So this was a navigation aid.
Right.
And
land here.
Yes.
Land here.
The whole operation of this spacecraft was amazing. It was just amazing to watch, and the execution of the maneuvers were spot on. They really were.
When you're painting a target to land on that's 10 centimeters, that's telling me you've got some precision that you can hit that.
Yes. I mean, they really did some innovative engineering and operations here.
Awesome. Cool.
Yes, Hybe-Satu spacecraft follows this target marker with like camera, and when the Hybe-Satu become close to the surface, then Hybe-Satu have flash lamp. Then it using flash lamp, then the retro-reflective marker becomes very bright in the image. But
nice.
In this case, the observation is held like at 20 kilometers away from the Ryugu, but in the opposition of situation, the sun is at the behind the spacecraft. So in such 0-degree situation, the target marker shines with the solar light. So it observed in this image.
Very easy to find.
Yes.
Very nice.
Yeah. So, this is not a finding in, I mean, scientific things result, but it is very interesting to see.
Yeah,
this,
it's interesting.
Images are good. Images are good. Very nice. Very nice.
Yeah.
Okay, let's slide down back to the conclusions and see if there's anything else you would like to cover out of these top 10. We've got a top 10 list here.
I think he's covered quite a few.
He's covered quite a few. We've covered this one. Yeah, we've covered the B-X, covered the dark ruggles. Yeah, the polar regions, we covered that. So yeah, we covered. Is there anything else you would like to cover, Yasu?
Oh, yes, I'd like to mention this number 3. Because it means in the previous studies, previous studies reported that there is some kind of difference between Eastern Hemisphere and Western part of Ryugu. There is some reflectance difference, but we found that in the opposition situation, yes, the number 3, but
sorry.
Yeah, in the opposition situation, we cannot find the difference between East and West. So we are thinking that the East and West direct difference which found in previous studies might be due to the photometric effect. I mean,
Yeah.
it can be seen in different phase angle observation.
So, Yokota-san, would you say it's the difference seen at 19 degrees phase that is not seen at 0 degrees phase is because of the roughness at the small scale and not composition?
Yeah. Yes.
So by noticing, hey, we see a difference at 19, but we don't see it at 0, it's telling us that it's the structure in the regolith that's different.
Yes, yeah.
And not the composition.
Yes. Cool.
Yes. Yes. So yes. Thank you, Deborah, for pointing out correctly that so I and Deborah and other colleagues are now focusing this point for next research to to make clear how the such photometric effect, I mean roughness, is distributed on the Ryugu. So this is our next analysis.
Awesome. Look forward to seeing that. I look forward to seeing that. Very good. Anything else you would like to cover?
No, I mean, there's many interesting thing is still on these maps, but I think most important things we already introduced here. So thank you very much.
Well,
so there are still some scientific gems in the paper, but we recommend go read the paper.
Absolutely. So it's like, well, you can either watch sort of some of the highlights of the movie, or you can go watch the whole movie. Go watch the whole movie.
Yes, go watch the whole movie.
Go watch the whole movie. So very cool. Yeah, Sue and Deborah, thank you so much for walking through this very lovely article on Ryugu. And you hinted at it a couple of times, So let me ask, where do we go in the future? What are the next steps? So for example, one of the ones you kept mentioning was when the sample return analysis comes back. When does that come back? Does that come back in 1 year, 5 years, next week? And so where do we continue this research with on Ryugu?
So the sample analysis groups have been broken up into different teams. I'm affiliated with the STONE team. I know that they are doing their analyses now. They're doing lots of their measurements now.
Cool.
We hope to have at our science team meeting in January hearing about these sample analyses. I suspect they'll appear in the literature in the spring.
Nice.
Papers will be showing up in the spring.
Nice.
And then it will be okay. Let's team on how to. So what Yokota-san and I do is look at the remote sensing data. So once the sample analyses have been published and they're out, then it'll be forming teams to merge the sample analyses with the remote sensing. But I think Yokota-san mentioned what are the next steps with the remote sensing data. I mean, this is a very rich, plentiful data set, and we're not done. So
like paper one.
Yeah, this is just paper one. Maybe Yokota-san could talk a little bit about where we're going next with our remote sensing studies. He's mentioned it briefly, but you want to give a little more detail, or?
Well, I think Deborah-san already explained important parts, so
okay.
I do not have much to add, but well, what kind of?
Yokota-san mentioned that we're looking at east versus west.
Yeah.
So we're trying to focus more on regional differences and what are the sources of the regional differences. That's going to be really important when we try to extrapolate what we know about the landing sites to the remainder of the surface. Is that fair to say?
Yes. Yeah. Yes. No. In this article, we only use the zero phase angle data, but there's many phase angle data left. So
right. I was going to say
using
okay.
We use much large range of the observation angles, and we get into not only albedo but also roughness or such kind of effect in detail, and we are still using the only low resolution data, which is observed at 20 kilometers away from Ryugu. So we have to do much high resolution, close observation data in future.
Nice. Thank you. Yasu, Deborah, I want to thank you one more time very much for walking us through Article 1 on this analysis. And thank you, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.
Thank you very much. Bye-bye.
Thank you. Bye-bye.